We're going to look at equilibrium mathematically today. So the equilibrium expression for a reaction is written by the mass action expression, where the Q value is based on the balanced equation. So it's the ratio of the products over the reactants. Okay, and these values are unitless because each term represents the ratio of the measured quantity to its thermodynamic standard state quantity, so that those units would cancel out. And Q and K can be written in terms of concentration, if it's a QC or a KC, or in terms of the partial pressure of gases, and in that case it's called a QP or a KP. And typically it's easier to measure the pressure of gases than their molar concentration, so that's why you have these two different things. And again, make sure you know which one you're dealing with so you know which values to use. So what's the difference between a Q and a K? So a Q is at any point in time, and that constantly changes until equilibrium. So the Q for the page 1 system, So if you look up here at the top, this is from your note sheet page 1 equation, so that's the example that I'm going to use down here. So Q is going to be products, so this one only has one product, which is the NO2. So the partial pressure of NO2, and that would be squared. So they use parentheses for gases. And then the reactant is N2O4, and that has a coefficient of 1, so the pressure of N2O4. And again, whether you use parentheses or not here, there's no power, so you can or don't have to use that. Okay, if we do it in terms of solution concentration, so we'd have to know the volume of our container and the number of moles to do that, we would use brackets. Anytime you see brackets, that's molar concentration, so it would be the concentration of NO2 squared over the concentration of N2O4. You would use brackets on that one just because that means concentration of. So if the reaction is a little bit longer, like you see here, so the lowercase letters would be your coefficients, so A plus the coefficient of B in equilibrium with the products, C with its coefficient, and D with its coefficient. They're going to all be part of this equilibrium expression, provided that their subscripts are AQ or gas. So if you have something that has both, you've got to make a decision. Are you going to measure pressure? So if they're not all gases, I can't really measure. I have to go with concentration. So again, it's going to be determined by the type of materials you have. So your Q expression is going to be this. So again, big difference between this and kinetics. So in kinetics, we can't use the coefficients of the balanced equation. In equilibrium, we have to. And if you think about this, it's logical because you're looking at the stoichiometry of these reactions. So if I have 2 of these to 1 of these, that obviously is going to impact differently if I need more of it. Okay. Now, next question is, why don't pure solids or liquids appear in your mass action or equilibrium expressions? They don't have pressures or concentrations. So looking at a couple examples, so this is asking for the Q in terms of pressure. So you'll notice I have gases and a pure liquid. So water can't have a concentration. As a gas, it could have a pressure, but since this one specifically states liquid, my Q value would be the pressure of CO. And one thing you should check is the equation balanced. So there's 2 hydrogens to 2 hydrogens. 1 carbon to 1 carbon, and then there's 2 oxygens, so 1 plus 1. So that's always something you should check. So I'm going to have the pressure of CO and the pressure of CO2 times the pressure of H2. If I were doing it as a Kp, then I would change those to concentrations of CO, concentration of CO2, and the concentration of H2. Okay, example B, you'll notice I have two solids. Okay, I have one calcium, one carbon, and 3 oxygens, 2 plus 1, so this one's balanced as well. So this one, your QP is just the pressure of CO2, so you will not have any numerator because this is a solid. So you got to be careful. Phase notations are really going to matter. And then my KP for this one is going to be, oh, you know, I messed up. This is KP. So this one, sorry, I was thinking this is just changing it to equilibrium, sorry. The last part was KC and I just followed suit, so. Okay, I need the parentheses there just to keep them straight. So then this one, the equilibrium would just be whatever the pressure of CO2 is. Okay. All right, going on to side 2, you'll see I think on your copy, these directions are gonna be on the back. So we're gonna do concentration. So first thing we're gonna do is balance these equations. So I have one calcium with one calcium. You might remember this trick from balancing. I'm gonna write water HOH since I have hydroxides and hydrogens. I'm gonna balance those last. Chlorines, I'm gonna have 2 of those. That's going to give me 2 of the H. Remember, that's the first part of my hydrogen, and then 2 of the hydroxide. So it will be 2 of those. So my QC is going to be, again, water doesn't count because I can't have a concentration of calcium chloride over the product of the calcium hydroxide and the product of hydrochloric acid, and that one has to be squared because of the coefficient. Okay, if I'm doing it at equilibrium, you're going to see basically the same thing. So the only difference between those K and Q is any point in time, K is at the equilibrium point. So when these concentrations no longer change. Again, exactly the same, it's just the time frame that's different. All right, next one we're looking at of aluminum nitrate plus water. So this is really dissolving this compound. So I have aluminum, I have 1 of those, and then I have 3 nitrates. Okay, so you know the water's not here, but remember these water molecules are surrounding these ions, and it really doesn't matter how many of them there are because water's not going to appear, and the aluminum nitrate is not going to appear in my reaction quotient or my mass action quotient. So this is literally going to be the concentration of the 2 ions, and the nitrate will be cubed. And then at equilibrium, you're going to see same thing, concentration of aluminum ions times the concentration of nitrate ions. Okay, and there is a special name for these solid ones that actually is called KSP, so we'll see that later as well. And that's how you write the reaction quotient.